Dobry wieczór Państwu. W imieniu Centrum Nauki Kopernik chciałbym Państwa powitać na wykładzie popularno-naukowym profesora Hanocha Gutfreunda na temat teorii względności, historii teorii względności i rozmaitych przypadków, które były związane z ich odkryciami. Dzisiejszy wykład związany jest z 100. rocznicą, plus minus kilka dni, publikacji jednych z najważniejszych artykułów naukowych w XX wieku. Artykułów, które zmieniły to, jak rozumiemy fizykę i to, jak rozumiemy świat, który jest wokół nas. Mam też przyjemność powitać na wykładzie profesora Łukasza Turskiego, fizyka teoretyka i przewodniczącego Rady Naukowej Centrum Nauki Kopernik oraz moich przełożonych dyrekcję Centrum Nauki Kopernik. Dziękuję też Państwu bardzo, że zaszczycili nas Państwo swoją obecnością i mam nadzieję, że życzę Państwu udanego wykładu.
Dobry wieczór Państwu. Profesor Hanoch Gutfreund, jak wszyscy z Krakowa, doskonale mówi po polsku, w związku z tym wstęp dziś będzie po polsku. Ja też jestem z Krakowa na przykład. Proszę Państwa, zebraliśmy się dzisiaj, żeby w bardzo ładną rocznicę obchodzić, a właściwie nie tyle rocznicę, bo dziś mija 36 528 dni od dnia, w którym Albert Einstein upublicznił teorię, którą dzisiaj nazywamy Ogólną Teorią Względności. Tak się jakoś złożyło w historii, że obie teorie względności, Szczególna Teoria Względności i Ogólna Teoria Względności, pojawiały się w momentach, w latach, które były niezwykle istotne z punktu widzenia historii naszej cywilizacji. W 905 roku, 905 rok, kiedy pojawiła się Szczególna Teoria Względności, to był rok, kiedy rewolucja wstrząsnęła podstawami carstwa rosyjskiego, a brylant z korony carskiej, bałtycka flota, została rozbita w pył i proch podczas bitwy pod Tsushimą. W 915 roku, kiedy Ogólna Teoria Względności ujrzała świat, cały świat cywilizowany był już od roku splątany w jednym z największych szaleństw XX wieku, I wojnie światowej. Nauka, te konwulsje polityczne przełomu XIX i XX wieku splatały się również z powstawaniem nowej nauki. Tacy specjaliści od teorii o nauce mówią, że nauka rozwija się poprzez albo, jak chce Kuhn, zmiany paradygmatu, albo jak Schumpeter przez krytyczną destrukcję. Ja mam takie wrażenie, że Ogólna Teoria Względności, jak i Szczególna Teoria Względności, a także mechanika kwantowa, to były wydarzenia, które powstały ani poprzez zmianę paradygmatu, ani poprzez krytyczną destrukcję. One po prostu zmieniły świat. To były wydarzenia zmieniające nasz świat. I trudno byłoby znaleźć lepszą osobę, która by o tym, jak teoria względności była przyjęta przez społeczeństwo, jaki miała wpływ i jak pewnie wydarzenia historyczne miały również wpływ na naukę na początku naszego stulecia. Trudno było znaleźć lepszego wykładowcę niż naszego wielkiego, serdecznego przyjaciela z Jerozolimy, Hanocha Gutfreunda. No i proszę Państwa, Hanoch jest nie tylko wybitnym fizykiem, jest również, chyba mogę tak powiedzieć, historykiem fizyki. Jest w tej chwili kuratorem archiwum Einsteina na Uniwersytecie w Jerozolimie. No i jest naszym wielkim, wielkim przyjacielem i proszę Państwa, tak się składa, że to nie jest jedyna rocznica w tym roku, to jest również 80. rocznica urodzin Hanocha Gutfreunda. W związku z tym w Państwa imieniu i w imieniu nas wszystkich w Centrum Nauki Kopernik chciałbym złożyć mu najlepsze życzenia I takie chyba najgłębsze życzenie, jakie mam, żeby nasze spotkania i współpraca mogły się jeszcze odbywać przez wiele lat. Profesor Hanoch Gutfreund jest również sportowcem. Jest biegaczem. Biega. I o dziwo biega również, kiedy odwiedza nas w Warszawie. Jak Państwo sobie łatwo mogą wyobrazić, bieganie w Warszawie to nie jest to samo, co bieganie w Jerozolimie, szczególnie jeśli chodzi o temperaturę zewnętrzną. W związku z tym ja już skończę, ale chciałbym poprosić Irenę Cieślińską, wicedyrektora Centrum Nauki Kopernik, żeby od nas wszystkich i od Państwa i od nas w Centrum Nauki Kopernik wręczyła Hanochowi ekwipunek biegacza polarnika przygotowanego do biegu w Warszawie.
To nie jest ten ekwipunek, nie?
A to jest
ekwipunek biegacza polarnika. A z kolei ja bym chciała życzyć, patrząc na te tłumy, żeby Twoje wykłady zawsze inspirowały takie tłumy do podziwiania nauki. I wielkie dzięki. Co jest tu?
To jest ekwipunek.
Zakładasz i biegniesz.
Nie. Temperatura w tej sali jednak nie jest polarna, w związku z tym... to zobaczyć, demonstracja. No Hanoch, to będzie po wykładzie, bo teraz jednak przejdziemy do wykładu o ogólnej i szczególnej teorii względności. Panie i panowie, profesor Hanoch Gutfreund.
Tak, to już otwarte? Tak? To dobry wieczór i już wszyscy wiedziecie, że ja mówię po polsku i mówię po polsku tylko dlatego, że moi rodzice do końca życia między sobą mówili po polsku. Ale nigdy między sobą nie mówili o teorii względności. I dlatego żałuję, ale wykład będzie po angielsku. So now you know that I speak Polish, and you also know my age. But I don't. How many of you were yesterday at Kip Thorne's lectures here? Oh, not many. Well, those who were, and maybe those who were not, know that if I would now go on Interstellar and come back after 1 year of my life, all of you will be 80. So there is an option. So now let us begin. So as you know now, this is it. So first of all, I would like to say a word about the 3 logos on the top. So first here we have the logo of our host institution, and next to it is the logo of my institution, and the logo here is a combination, a graphic combination of 2 Hebrew letters, which are the initials of Universita Ivrit, Hebrew University. And this is the logo of the Albert Einstein Archives at the Hebrew University. So this lecture, in a way, is a co-production of what we are talking about. And you see, the whole world celebrates what Professor Tursky already told you. And because Albert Einstein, in his last will and testament, gave to the Hebrew University all his wealth. And his wealth is not material wealth, not financial wealth, it is only his intellectual wealth, his papers, his correspondence, his manuscripts, and he made us, the eternal home of his intellectual legacy. And therefore, when the whole world celebrates, we participate. And we produce exhibitions. And we were this year in Rome. There was a big event with an exhibition, and the opening was attended by a representative of the Vatican and the chief rabbi of Rome. So can you imagine something more spectacular? And we have one in Berlin, and we now have an exhibition, na ulicy Pastera 5, in the Library of Physics, with some documents, because there is a conference also here. So I will take you now through this historical odyssey. So this will be the first part. Once we get to the thing that we celebrate, we will talk about what Professor Tursky promised, the implications, the reception, and a lot more. So you see, this gentleman here, he tries to fill his cup with coffee, and he's sitting on a train, and he wants to know, the windows are closed, and the train moves or does not move, or moves slowly or fast, but at constant velocity, and he does not miss the cup. So by this experiment, he cannot tell if the train moves or doesn't move. And this was known already to Newton and Galilei. This is a mechanical experiment. That no mechanical experiment that you do on such a train will tell you. But in those days, people thought that electromagnetic experiments will make the distinction. And it was the great insight of Einstein who said, no, there is nothing that you can do on such a train that will tell you the state of motion of the train. And this is the principle of relativity. And Einstein already made a first generalization by including all phenomena of nature. And when he added to this the assumption, which was not obvious, it was a very bold assumption in those days, and nobody dared to make that assumption to solve all the kinds of puzzles in physics, that the velocity of light is constant. He then could derive these three results. That means if two observers that move with respect to each other measure a length of the same rod, they will not agree on the result. If they look at the same clock, they will not agree on the time between two intervals. They will not even agree on the order of events. And if you know this, then just with a chalk on a blackboard, simple derivation, line after line, every step understood. The greatest pleasure that I had as a teacher of physics is taking my students, young minds, for the first time, telling them this and showing them in a short time that everybody understands how this happens. Yeah. So this was done by Einstein in 1905. And what you have on one slide is the entire special theory of relativity. Everything else follows. And now Einstein did it in 1905, which is called his miraculous year. And people talk about miracle because he did then much more. He also wrote an article about the nature of light, the particles of light. He wrote an article where he explained this Brownian motion. In 1 year, this young man constructed the pillars of modern science and the basis for the three major branches of science: quantum physics, relativity, statistical mechanics. But in my view, this is not the miracle. The miracle is that we are talking here about a young man, 26 years old, not working at a university, fully employed in a patent office. That means that everything he did in his free time. But think about this free time when he has a 1-year-old baby sitting in his lap when he comes home. So this is also a miracle how he did it. So this was the special theory of relativity. And everything that Einstein did in 1905, if not Einstein, it would have been done maybe not in 1 year, not by one person, because everything that happened in 1905 was in response to things, to questions on the agenda of physics. Physics was in crisis. There were new experiments, there were observations, classical physics could not solve them. Einstein in that year solved everything. But then why? And this is a question. Why did he think that he has to generalize it? Why did he go to the general theory of relativity? There was nothing in that motivated it. There were no experiments that served as a constraint to construct a new theory. No empirical or observational motivation. So on what knowledge did he construct this theory? Because you see, everything that is today connected with general relativity, the bending of light, redshift, expanding universe, gravitational lensing, black holes, everything that Kip Thorne talked about yesterday, that all came later. That is a consequence. There was one tiny little effect that existed, but most physicists ignored, and there could have been other explanation for that, and that is this motion of planet Mercury, which instead of going in an elliptic orbit, fixed in space, as Kepler and Newton would want to have it, astronomers found that it precesses. By how much? By about 1.5 degrees per century. But most of that could be explained by Newton. 43 seconds of an arc remained unexplained. Now think about it. This in itself is a miracle. In those days, without computers, with those technologies, astronomers could observe and calculate with such confidence and precision that everybody believed when they told us that 43 seconds are not explained by Newton per 100 years. And Einstein hoped that in 1907 already, when he started his Odyssey, that the new theory, that is what it will explain. So the special theory of relativity, applies only to constant velocity motion. It is incompatible with Newton's theory of gravity. I don't want to elaborate on it much. This is not enough to compel somebody to launch such an effort, because there is no experiment and there is nothing to guide you. But what did Einstein tell us? In a booklet that he wrote several years later, he said, since the introduction of the special principle of relativity has been justified, every intellect which strives after generalization must feel the temptation to venture a step toward the general principle of relativity. Now, I emphasize 2 words here. First, every intellect. There were many intellects. There were giants of physics. They did not venture that. Some tried, but gave up very soon, or went wrong path. Must feel. He feels compelled. He feels compelled because it is inconsistent. You have now 2 theories which are inconsistent: Newton and special relativity. So regardless anything, the aim of science is to generalize, to find unifying principles which explain different phenomena in one framework. And this is what compels him. So now he says the following. You see, I should say, before I show you this famous picture, I should say the following. You see, he wants to generalize it also to accelerated motions. But if the train accelerates, then the coffee will not get into the cup. If it suddenly accelerates, he will miss the cup. So how can you say that accelerated motion is equivalent also to non-accelerate, to uniform motion? And this is the ingenious insight of Einstein. This. And therefore, I want to explain it to you better. Now gravity comes in. And gravity comes in, and he's reminded of this mythological story about Galileo throwing objects from the tower. He never went up to the tower to throw objects. He didn't have to. He knew that they will fall at the same time. He even explains why they have to fall at the same time. It's a very ingenious explanation, but it is beautiful to maintain this legend. So he went up there, and all objects fall at the same time because they are pulled to the earth by gravity, and gravity is the only force that imparts the same acceleration to all objects. Newton knew it, Galilei knew it, everybody knew it. Only Einstein understood that this is something deep, that this is a key to a completely new physics. And what does it mean? So now look at this lady. She is in a rocket, and the rocket is accelerated upwards, and she drops two objects, different weight, and the objects will hit the floor at the same time because she drops it, and meanwhile the rocket gets up. So the floor, of course, reaches the objects, and she sees that the objects reach the floor at the same time. Now, if this rocket would not be accelerated, would be on Earth just in the gravitational field, she would do the same thing. Still, the objects would fall at the same time. How does she know? If she is rocketed up into space or at rest on the surface of the Earth or a gravitating field. So the answer is, not only she doesn't know, she cannot know. She cannot know because gravitation and acceleration are equivalent. The equivalence principle, accelerated gravitation, and later Einstein referred to this as the happiest thought in his life. And the way he describes this happiest thought is also interesting. He says, I was sitting in my office and I saw across the street somebody working on the roof of the house, and suddenly I thought, what will happen if he falls? So I thought, if he falls, he doesn't feel the force of gravity. Why doesn't he feel the force of gravity? We know. Because if he doesn't fall, he stands there, he throws two balls, they fall with respect to him, so he knows there is gravity. But when he himself falls and he drops the balls, they will not fall. They stay at rest with respect to him, so there is no gravity to him. And this is the key to everything. And this is the happiest thought, so let us see this equivalent principle, how he uses. Immediately, the bending of light follows. Because if you have this, you have the same rocket, and you have here a hole, and the ray of light gets through this hole, and by the time it gets to the other side, the rocket is propelled upwards. So you see somebody who is in that rocket sees that that the ray is bent. But if you have the equivalence principle, that means that the same has to happen in a gravitational field. So you have this thing, this great surprise. He doesn't know by how much, but he knows the effect. So this is the bending of light. Now comes the other thing. Suppose you have a disk, and you measure the circumference of a disk and the diameter of a disk. How do you measure? You take unit measuring rods and you put them on a disk. Now suppose that this disk is now rotating. With respect to you, if you stay outside of the disk, then special theory, you remember special theory about the relativity of length, will tell you that the rods are shortened. If the rods are shortened, that for you, you need more rods to put on the circumference to measure. Therefore, it's longer. And if that is the case, you lose the basic result of Euclidean geometry. So you see, linear acceleration is gravitational field. The rods that are accelerating. Acceleration is equivalent to gravitation, and rotation gives you non-Euclidean geometry. Now suppose you do the same experiment with clocks. You have your rotating rod, your rotating disk, and you put a clock on the circumference and the clock outside, which is synchronized with the clock here. They don't move with respect to each other. Special relativity tells you that this moving clock will go slower. But this moving clock is now in an accelerated frame, which is equivalent to a gravitational frame. That means that time moves slower in a gravitational field. All of Kip's lecture yesterday was based on it, and that is what will make me so young if I go an interstellar for 1 year, as I told you before. So now what does it mean if you put a clock here on Earth and you put a clock up there, Now these are atomic clocks. In an atomic clock, in a clock on your wall, there is a pendulum which measures time. In an atomic clock, it is the motion, the electronic motions, and those atoms emit certain lights. And these atomic clocks now here moves. This doesn't work, can you? Okay, yeah. These atomic clocks here move slower than here. That means that the frequency now is lower. That means that the light is moved to the red side of the spectrum. This is called the gravitational red shift. And this phenomenon was verified. Kip Thorne told us about verification between such two clocks. In 1959, two physicists made an experiment. They put one atomic clock at the bottom of a tower in Harvard, 22.5 meters high, and the one on top, and they verified that the one at the bottom runs behind the one on top by 1 second in 30 million years. Now, that is enough. That is enough to make it absolutely important for our GPS system. Of course, then it is not 22.5 meters, and the GPS system is measuring time of signals that go from us to the satellites. So you see, GPS, if we did not have general theory of relativity, we would not have a GPS system. So now we know that physics is geometry. And gravity modifies the pace of clocks and the length of rods, and therefore it affects the geometry of space, and Einstein is compelled to abandon Euclidean geometry if he wants to have his new theory. And later he even writes in in this article that geometry is a natural science that may be regarded as the most ancient branch of physics. And it is experiment which will decide which geometry we have. And now, general relativity describes gravity in a purely geometrical terms, and there is this famous saying that matter tells space how to curve space, it's space-time actually tells matter how to move, and so what we need, I mean, for these two parts, we need a field equation. We need an equation which tells you what are the properties of space-time, and we need an equation of motion that will describe the motion of particles in such a gravitational field. And Einstein, and his challenge, of course, is to find both, to describe the motion of bodies, to describe the geometrical structure, and he has to do it so that, that the equations that he finds will respect his quest for general relativity. Therefore, that all descriptions, all systems of coordinates, all modes of motion, the laws of physics have to be the same, and in addition, these equations have to satisfy known physical properties, not going to go too much into that. And then he realizes that he needs mathematics, and he doesn't know mathematics. You see, the mathematics that Einstein knew, and Einstein used in 1905, is barely high school mathematics. Now he needs something very sophisticated that was already developed by mathematicians. So he calls his friend Marcel Grossmann, who is then a dean in Zurich of mathematics. You have to help me or I'll go crazy. And the two of them work together for several months. And Einstein fills a notebook, dozens of pages. This we refer to it the Zurich notebook, where he learns differential geometry, tensor calculus. And he writes to his friend, Sommerfeld, an illustrious physicist. He writes to him on what he is working, but what is interesting here, and that he now gained an enormous respect for mathematics. Until now, he thought that this is luxury. Kip Thorne yesterday made a very similar remarks, almost using the same words, that is only through working on what he's working that he learned how to respect mathematics. He did not, I told him about this letter, he did not know this letter, and he was very happy that he had that he went through the same process in that. And I'm showing you 2 pages. And there are dozens of pages. There is hardly any text in those pages. This is it. And lo and behold, in these 2 pages is the final solution, the correct solution. And here is an expression, and you see Grossmann is also mentioned there in his handwriting and in the other hand. And for those of you who know something, there is a Riemann tensor, there is a Ricci tensor. This is the correct thing. And Einstein misunderstands, misinterprets that. He believes that it does not fulfill the physical requirement. And he abandons it. And from that moment, for the next 2.5, almost 3 years, he makes every mistake possible. Because he convinces himself that this is the best that one can do. He then publishes with Grossmann a paper. For those of you who can read German, in the title here, note, the title here, this is a guideline of a theory, but this does not mean the general theory of relativity, but it means a generalized theory of relativity. So he's very careful here. And here, you know, this is also a nice quotation. At that time, Einstein has a passionate love affair with Elsa, who later became his second wife. And he confides in her. Look what he writes to her. He's so happy. He worked so hard, he has to rest, otherwise he will go kaput. And these equations are not what he wanted to have. But then he finds an argument after argument, convincing himself and the whole community that this is the correct result, the only result that physics allows, that physics does not allow general covariance, that this would break all kinds of physical principles, all of them wrong. In the middle, he also makes some mistakes in derivations. And all that lasts until November 1915. And in November 1915, during the summer, he already begins to see the light. And then, week after week, he publishes an article. And the first one already gets him closer, the second one gets him a little closer, the third one, and what we celebrate is the one, November 25th, and this is the equation. And this is, I will show you, I will say something about the equation. And the equation is very easy to understand. And on the right-hand side, this is a mathematical expression of all the matter in the universe. And that matter in the universe determines the properties of space-time, and the properties of space-time is represented by the left-hand side, and that is enough for you to know now. And that is it. But I will show you a little more about this equation. So then he writes this beautiful manuscript, 46 pages. And there is a charm in manuscripts, believe me. In the archives, I look at manuscripts. Now, there was a philosopher, Walter Benjamin, and he wrote an article, What Will Happen to Art at the Time of Mechanical Reproductions? When we will do all the kinds of things, so what is the value of an original? And he said there will always be the value. Even if nobody will make the difference, it's enough to know, because you identify with the place and the person and the time. The same thing applies to this. So this is, we have these 46 pages. This is Einstein's photo in 1916 at that time. And the last page here, it gives the result, the bending of light. He predicts that it will bend. He predicts the ending of the angle of the bending of light. And here he predicts, he does the calculation. Remember that 43 seconds? There is 43 seconds here, somewhere here, or 43 seconds, you see? He gets it on the nose. And we get that, what happened? When he gets that, he almost gets a heart attack. So this is, in a way, when that was confirmed in 1919, I'm jumping 4 years ahead, time of a solar eclipse, all the newspapers in the world come with great headlines, and you see particularly the one in New York Times, a book for the 12, what is that? Einstein's theory, a book for 12 wise men, and that has to do with the myth that only 12 people in the world, originally it was only 3 people in the world understand general relativity. At that time already only 12. Today every student of physics who has a course understands general relativity. So this was it. And Einstein, when that happened, by the way, Einstein from that moment became a world celebrity. Before that, he was known in physics, but not by the general public. Here, he is known overnight by everybody. People say that if you today take Madonna, Elvis Presley, Michael Jackson, put them in one person, that's what Einstein was on that night. And we can also speculate why, but I will not do it now. So this is the end of the story, but not the end of my talk. So this is the end of the story. So this gravitational field theory, which was completed, a result of a very convoluted, laborious process, which brings together Newtonian theory and the concept of space-time. And this is not the end, of course, but this illustration is so nice that I cannot not show it to you. And yesterday you heard what happened in the next 100 years. This is, of course, the beginning of many things. Now, what happened immediately after that? Immediately after that, it is physicists, mathematicians, astronomers, and philosophers all joined this boom in their intensive debates and controversial discussions. And more of leading physicists turn their attentions, and basic ideas and principles are refined. And the first solutions of the field equations are derived. And Einstein himself makes further contributions. He is the first to realize that this equation has to apply to the universe as a whole. And that insight, not what he immediately did, that insight is the beginning of relativistic cosmology. And 2 years after that, there are fierce debate between Einstein and a Dutch astronomer De Sitter, German mathematicians and physicists Klein and Weil, and these four exchanged 35 letters between them in 2 years, and we have all the 35 letters, and I was fortunate to read them. And there is nothing like reading that compared to reading the papers that were published. Because that is where the drama, where everything happens, where this interaction. And as a result of that, that was the beginning of and Einstein was not the main player. He's very stubborn. He would like to have a static universe, not a dynamic universe, and all kinds of things happened. So these are the formative years of general relativity, which made it evolve to a pillar of modern science with all its consequences. And in those years, you see the shift of attention from the equation, because until now you have to have an equation. Now you are interested in the solutions. Now so the equations you had before, and but now I will now sit. Are you sitting in your seats? Yeah? You're not falling. Now I show you the equation, because this is a shorthand, right? So this is the equation, right? Now every g here is a function of 4 parameters, and you have many of them. And this is not all, because you have a sum of indices. So no wonder, as you heard yesterday, that this is a very complicated mathematical equation. We have very few exact solutions. We don't even have an exact solution of 2 bodies moving with respect to each other. So we have to do approximations. Yesterday you heard about the great challenge of numerical general relativity. Everything that we do, the prediction of waves, of gravitational waves, cosmological models, black holes and the physics of black holes, everything is here. This equation still holds many secrets which we haven't understood and uncovered yet. And no wonder that Kipps told us all the things that happened in the 100 years is from this equation. And all the things that will happen in the next 100 years will also be from this equation, which we cannot imagine yet. So this is the thing. So now, what happens? But general relativity also has its opponents. And the reception of the theory differs from country to country. And every country is a story. And I'll tell you a few stories briefly, because I promised that I will tell you something about the Polish story, which is a very interesting story in this context. So first, let us look at France, for example. Now, in France, in most countries, like France, Italy, Spain, particularly in those countries, the general theory of relativity for years was ignored by physicists, was taken up by mathematicians, by astronomers, by philosophers, and what Einstein objected most, by artists and people from literature who were so inspired by that and claimed that everything is relative. But Einstein objected, and he did not succeed. Einstein did not call it the theory of relativity, because this is the most misleading, the greatest historical misconception, calling this the theory of relativity. Because if anything that this theory shows, that not everything is relative. That the laws of nature are not relative. And that is the important thing. This is the essence. All right, so when you apply that in different circumstances, different people will see different times. But the laws are not. Einstein called it for years the theory of invariance. It's only later that it happened. Now, in France, only Paul Langevin was the only physicist who took it seriously and who defended it and who understood it. Others either ignore it. There was Émile Picard in a big debate organized by the Academy in France, who referred to this theory more as metaphysics than physics. Generally, it was the attitudes ranged from skepticism to objection. The attitudes were influenced also by images of science, by scientific ideologies, and not less by political attitudes to Germany 4 years after a devastating war. And all that played a role. Let's look at another example. Italy is a very interesting example because Italy is the home of the great mathematicians like Levi-Civita, and who did this mathematics on which it is based. And there, interestingly, not in other countries, the main issue of the debate was that this theory is conceived as a revolution. There were whole groups in the scientific Italian circles, mathematicians, physicists, who did not accept revolutions in science. Science proceeds steadily, step by step, evolves by arguments, things are correct and are supplemented, not revolution. And to counter these objections, everybody, including Einstein when he visited Italy, made a great effort to convince everybody that it is not a revolution, that it follows naturally from Newton. Interesting. Now we go to Germany. Germany is a special case because Germany has two elements. In Germany, first of all, the theoretical physicists, of course, are the heroes. The most active, they develop and they are involved. But then there is a group of physicists, particularly experimental physicists, among them two Nobel laureates like Philipp Lenard and Johannes Stark, who think that physics is only experimental physics. And theoretical physics is labeled by them as Jewish physics. And there is explicit anti-Semitism in the attitudes. When Einstein, in Berlin, every lecture, public lecture that he gave in Berlin, in 1918, 1919, there were groups of right-wing students demonstrating outside the hall. When Heisenberg, when Nazis came to power already, Heisenberg was called to Gestapo to explain why he teaches Einstein physics. So he continued to teach, but he packaged it differently and called it cleverly differently. So that happened in Germany, and because I could go country by country. Now, before I tell you the Polish story, with which I shall conclude my presentation, I just want to tell you that Einstein, he was a great scientist, but at the same time he was a missionary of science. And not once, many times. He gave public lectures. He gave a lecture to the workers in Berlin. He thought that workers should understand general relativity. He never refused those invitations. And one of the workers, this was the Communist Party in Germany, of course, and in one of these lectures, Brecht was present, was in the audience, and that is why we have this great play, The Physicists. He was inspired by that public lecture. So Einstein wrote a booklet, which we call the popular version. He said he has to write it. The theory is very simple, but people will not understand it if I don't explain it to that. So he wrote this booklet. It became a great success. This is a special and general theory of relativity, a popular version, or what they so gemeinverständlich, understood by everybody. This became a worldwide, until today, bestseller. First 5 years, there were 14 German editions. There were jokes. Einstein was not very happy. There were jokes that it is popular for students of physics. Instead of gemeinverständlich, he said one should call it gemeinunverständlich, which is not understood, and so on. And within about 10 years, it was translated into many, many languages. Here is a poster of many translations, and it is in Japanese. In Japan, it was published in June 1921, and it had 6 editions in 1 month. Almost everywhere. It was published in 1921. There is a Polish edition, and I shall talk about the Polish edition in a minute, because that sheds light on what I want to do. But before that, let me tell you that there was here a professor of history in the Jagiellonian University, Bronisław Średniawa, and he studied this issue of the reception of general relativity in Poland, of relativity in general, and of scientific and personal contacts of Polish physicists with Einstein. And there is a whole list, and I'll tell you why I singled out the 3 on the side. These are illustrious Polish physicists. They all had contacts with Einstein. The 3 on the right-hand side, I will say something more about them, because there were very intensive contacts with Einstein, even collaboration with Einstein. But people like Stanisław Loria and Władysław Natanson and Jan Weissenhoff were pioneers in Poland of the reception of physics, of the dissemination of physics, of writing about physics, of lecturing about physics. There was nothing in the physical community, like in the countries that I mentioned, France, Italy. The physical community in Poland, from the beginning, accepted first the special theory of relativity and the general theory of relativity. There were some dissidents, particularly among mathematicians. There was one mathematician, Professor Zaremba, who wrote against physics and against these unrealistic assumptions, but even he finally was convinced. There was some opposition among intellectuals. There was a little bit, there was the kind of ethnic attitudes. There were some, but not to the extent as in Germany. And this is a great story. And you must understand, I am not going to tell you, that this time, this is the time of Poland reuniting after more than 120 years of division, during which 3 separate centers of learning developed in Lwów, Krakow, and Warsaw, and they all developed their own tradition, and that had an effect. If I would study with you or explain in great detail the story, then that would also come in. So this booklet that I mentioned, o Szczególnej, Ogólnej Teorii Względności, was translated by a man, engineer Dr. Maximilian Huber. Now, Maximilian Huber was an engineer. He was not a physicist. He understood relativity, And he did for the reception of relativity in Poland more than anybody else. He, in public lectures, he was involved, by the way, he, in public lectures, in popular articles, he argued the case of relativity, and he translated this booklet. And the interesting thing is the second edition of this booklet, not the first, because the second edition of the booklet in 1923, and I don't know, Andrzej Trautmann is not here, but I am grateful to him because he pointed to me this thing. He sent me a scan of this booklet from the library in Warsaw, and it is great. And you see that you can read, I have to you this Polish thing, that Polish introduction. And of course, it says that this is not a bedtime story. Yeah? It's not just, it requires an effort, but it is certainly worth the effort. And he also, it's a very long introduction. And there are very interesting additions to that. And for example, he understands why in Germany, he can understand why in Germany people's attitude towards general theory of relativity may be based on ethnic prejudices. Why? Because the Germans lost the war, have a terrible defeat, so they need a scapegoat. So they are angry. But in Poland, nothing like that can be justified, or nothing like that could happen. And he, of course, ends this introduction with something very passionate, a statement, patriotic, about our reunited fatherland. And now, just to finish, I promised you 5 minutes, okay? 5 minutes or 7? All right. Now, so just I want to tell you, because I mentioned these three Polish physicists, and one is very well known here, and that is Leopold Infeld. And Leopold Infeld worked with Einstein. What you see here, the correspondence that you have here, is the number of letters from Einstein to Infeld or from Infeld to Einstein over this period that we have in the archives. And this correspondence is rich, is inspiring, is very interesting. And here you have this short bio of Infeld, and he, for years, he was a brilliant student. For years, he could not get a job, so he was a teacher in some Jewish school in Konin, and then in a girls' Jewish school in Warsaw. But after that, he got a position in Lvov. Then he went to the United States. He worked with Albert Einstein in Princeton. The three of them produced one of the most important papers. Einstein, Infeld, and Hoffman, and this has to do with the problem of motion in general relativity, and I don't have time to explain to you what is the problem. It's an ingenious thing. Now, what is interesting about Infeld, that in 1950, Infeld returned to Poland. And he may be perceived as a rebuilder of theoretical physics in post-war Poland. And there are many of his students here. Of course, this was not very balanced because all his students had to work on general relativity, but he was a figure. And there is an interesting correspondence between Einstein and him from those years. Infeld writes Einstein that he has never been happier in his life. He trusts the government, he trusts the new regime, everything is open to him. He's, by the way, very happy that Stanisław Luria survived the war, and he writes to Einstein that he's now building a new physics institute in Wrocław. And Einstein responds to that. Einstein is happy that Infeld is happy, but he has his doubts. that it is so great, and this is a great correspondence. Now, the next one is Marion Mattison, who is less known. He died early. He was a brilliant physicist, brilliant. The truth is that Einstein offered this position in Princeton to work with him and Hoffman on the problem of motion first to Mattison. But for some reason, that letter didn't reach him, because then he was in Kazan, and therefore he, that's what happened. He worked with Hadamard, the great mathematician in Paris. He wrote one of the important papers on spinors in general relativity and motion generativity when he worked under Weissenhoff in Krakow in the late 30s. So this is a brilliant physicist. He also couldn't get a job here, so made his life by teaching Hebrew in the Jewish community in Warsaw. So you understand that in addition, the third one is Ludwig Silberstein. And the three of them, it so happens that they were all Polish Jews and great physicists. And the correspondence between them is you cannot separate their reference to, also in Einstein's letters, their reference to their Jewish identity and their implication of being Jewish, whether here or the United States or what happened with the Nazis coming to power. So it is all part of the same story. And there is a great, great physics, and Ludwig Silberstein is the third one who lived in the United States. And he was the advocatus diabolis of general relativity. All his life he tried to prove that he was a great friend with Einstein. They were great appreciation. They met. But he tried to prove that general relativity is wrong. He formulated first a wrong version of the special theory of relativity, different than Einstein's. And then over 3 years, in 1933, there was a bitter debate between Silberstein and Einstein on the so-called two-body problem. That I will tell you what it is. Silberstein claimed that he found a solution of that equation which has two singularities. Singularities means particles, massive particles there are, and it is static. Now you cannot have a static situation, because if there are two particles, there is a force of gravity, they should attract each other. So how can it be static? So he told Einstein, you have to correct your equation. So Einstein immediately showed him, no, you are wrong. And he showed him where he is wrong. But Einstein made a big mistake, which in his proof, which Silberstein was happy to point out to him. So Einstein thought maybe he is right, so we'll look at it. And then he sent him another correction. And he again makes an error, Einstein. So this was a long story. It ended in some bitter controversy and in apology letter between Silberstein. So this is the end, but I want just to conclude, because I remember that yesterday, when Professor Tursky introduced Kip Thorne, he told him a story about these two physicists coming from Berlin, Planck and Nernst, who came and they came with an offer to Einstein, an offer. They came to Zurich, an offer to Einstein. Einstein couldn't refuse it, and he went to Berlin. And Professor Tursky said that they were waiting there because Einstein lived on top of the hill there, for him to come down from the hill. But then he emphasized they were not waiting for him to come with the tablets. But Einstein with the tablets is not such a bad metaphor. That's it. Okay.
Dziękujemy bardzo za wykład. Mamy jeszcze chwilę czasu na ewentualne pytania. Tradycyjnie zaczniemy od tej części sali. Kto z Państwa chce zadać pytanie, proszę o podniesienie ręki. Nasi animatorzy podejdą z mikrofonem.
Thank you very much for the lecture.
Można zadawać pytania po polsku.
Dobrze wiem. Dziękuję. It is sometimes said that Einstein, when creating his general relativity, was under a very strong influence of Ernst Mach. Ernst Mach inspired Einstein to his equivalence principle, and there's even some evidence that. Yeah. Can you hear me well?
Yes, it's
yes.
a good point.
What
yes.
I'm asking is that it is sometimes even pointed that there is an evidence of a very early version of the equivalence principle in the works of Ernst Mach in his The Science of Mechanics. I'm also curious: does the archive of Einstein's correspondence contain also letters with Mach and related works? I've heard that it lasted until Mach's death in 1916. Do you have all that? And can you elaborate on this, please?
It's a good point. It's a long and important story, but I will make it short. Einstein was influenced by Ernst Mach to a great degree. In fact, without any empirical data to guide him, what he defined as Mach's principle was his heuristic guideline in formulating the theory. And Mach's principle says that Mach's criticism of Newton says that there is no absolute space and that all inertial forces, like centrifugal forces that you feel on a merry-go-round, that they have to do with the influence of all the stars in the universe. There is this famous bucket filled with water, yeah? And if you rotate the bucket, then the water makes a parabolic surface. Newton said this shows that this is something absolute. Mach said, no. If the bucket would not rotate, but all the stars in the universe would rotate, you would still have the same. Einstein adopted that principle. Einstein defended that principle until the end. All Einstein's controversy about the cosmological model, about the static model, about the closed universe, were all attempts to hold on to Mach's principle until, to his regret, he had to give it up. Others lost belief in it before that. This is simply wrong. And this is a very interesting point. This is not the only guideline. That was Einstein's heuristic guideline towards the theory, which had later to be abandoned. So think about this situation. You, after a long struggle, you get a correct theory, but you were driven by wrong guidelines. This is the case.
Dziękujemy bardzo. Teraz pytanie z tej strony.
It's okay.
Złamaliśmy symetrię.
I have a question. I have a question to you, because I am very surprised to see so many young people here. Don't you have anything better to do on Friday nights than coming here?
Z całą pewnością zarówno nasz gość, jak i inni nasi goście mają plany na dzisiejszy wieczór.
Tak. Okej.
Jedyny powód, dla którego zabieram głos, dotyczy tych tabletów.
Zginęły. Gdzie są te tablety? Zniknęły.
Jest taki dowcip, który nie najlepiej brzmi po polsku, lepiej brzmi po angielsku. Dotyczy momentu, kiedy Steve Jobs opuścił ziemię i dotarł do nieba. I święty Piotr mówi do niego: ach, świetnie, chwileczkę, Mojżesz. Zjawia się Mojżesz. Mojżesz, Steve pomoże ci zrobić porządek z twoimi tabletami. Więc to jako dodatek do tego wspaniałego dowcipu. Panie i panowie, mam nadzieję, że teraz rozumiecie, dlaczego tak lubimy spotykać się z Hanochem Gutfreundem w Warszawie i dlaczego, mam nadzieję, nie będziemy musieli czekać na następną okrągłą rocznicę Ogólnej Teorii Względności, na jego następny wykład, na który już wszystkich państwa dzisiaj wieczór zapraszam. Jeszcze raz wielkie dzięki i mnóstwo lat.
Dziękuję.